Great, thank you very much. So my name's Phil Bates. I've spent probably the last 20 years in Oracle making products. So I've made our business intelligence, led our business intelligence analytics and data visualizations teams originally up until about 2012. A lot of cloud engineering there as we embedded intelligence and analytics into pretty much every application that Oracle makes. And then took a short break to do a bit of particle physics, which is probably the craziest thing I've ever done in my life, is to go back and sit and learn how to do the integration required for fourth year and MSc particle physics. Quite fun though at Bristol University. And then came back to lead our cloud native engineering teams. So I've led our teams building Kubernetes and all the Kubernetes adapters into Oracle's cloud infrastructure, as well as my teams have led functions as a service functionality, including an open source project called FN, which I'll touch on briefly in here. More recently, I've started a program within Oracle, which is a global program that provides direct collaboration and engagement with researchers who are pushing the limits of computationally intensive and data intensive research and exploring how high performance cloud infrastructure can have a part to play in those kinds of projects. So I'm very interested to understand more and more about the kinds of use cases coming here. I'm also a visiting professor at of computer science at the University of Bristol, which is a more recent role that I've taken in conjunction with my Oracle work. What I'm going to do today is to talk about some of the projects that we've been supporting from Oracle with researchers using cloud to do things that previously probably you wouldn't have considered using cloud for. I'm going to talk briefly about what our cloud is, right? So we've had some people mention bare metal and HPC in the cloud. I'm going to talk about what Oracle's public cloud infrastructure with respect to those areas are, and the kinds of technologies that researchers are using from us to put their research workloads into cloud. And then I'm going to explain the program and a couple of the projects around it. So I quite like starting off with a demo. So one of the projects, actually before we even launched the Accelerator, that I've been working with from our development teams is a project with computational chemistry team at Bristol, and we published a paper in Science Advances in June, July last year to be able to look to see whether we could take the physics engines being used to do real-time simulation and visualization of quite large molecules in some cases, right, using VR, right, to enable researchers to go into the molecules and explore with them and see whether we could do that in a distributed cloud environment. The paper itself was focused on seeing whether VR and cloud would actually help people be able to understand molecules more effectively, or was it all just hype? And so what we did is we took a whole bunch of different molecular modeling activities. Sorry, just start the video. And measured, right, how quickly people could perform tasks using traditional two-dimensional, three-dimensional, and four-dimensional interfaces. So in this case, we've got a Fulminster-Buccarine molecule being passed around in VR between two researchers with the physics engine solving all the calculations in real time, right, all the times the forces are going. This is passing a methane molecule through a carbon nanotube, okay, which is another one of the molecular modeling tasks that we measured hundreds of students and researchers going through. This was changing the helicity or the screw sense of helicene, okay. And this one here is tying a knot into a peptide, which many people have asked me since, why would you tie a knot into peptide? It turns out that proteins, peptides, etc. are often not in nature, and that totally changes their pharmacology. So we measured these against 2D interfaces, 3D interfaces. We produced it as a collaborative framework so that multiple people could work together. In this case, you've got two researchers, two postdocs passing a molecule between each other, but they don't even have to be in the same physical room. We've had people in Barcelona, Bristol and Dublin all going into the same VR environment with the physics being solved all in one place in a data center in Frankfurt. So the paper was really interesting. It came up with some results which might be predictable, might not. One of them was that for certain activities, VR makes no difference. If you have a very two-dimensional things, like changing the clockwise, changing the screw sense of helicene, pretty much the same as a 2D interface, because it's not difficult to create a circle like this with a mouse. But for tying a knot in a peptide, 30-fold improvements in speed. Most of the people couldn't do it in 2D. Everybody did it in VR. So we demonstrated real tangible evidence that these new kind of interfaces can make a real difference, as well as introducing this cloud platform to be able to do it. The team, these were fairly small molecules in order to be able to sort of demonstrate the applicability of VR, but the team's also using cloud to do quite large ones. This is an example of trypsin binding of benzamidine. Okay, and you can see here that the infrastructure is hosted on cloud. What they've been able to do is to use cloud to create the kind of infrastructure for a given kind of experiment. Small molecule, VMs, couple of CPU cores. Large molecule, big series of GPUs, right, doing all the solving in real time. So you can see in this case they're taking the benzamidine and getting it into the docking site. There's somebody playing around with that, seeing how the geometry of that works in real time. Okay, and we've since gone on to work with this team across a whole series of different kind of molecules and with industrial partners coming in to get involved as well. Just go to the next slide. Some interesting results that came out of this. I thought this project wouldn't work. I really like research projects where the objective isn't to get it working, it's to see if it's even possible, right? Which means you've got to try things that probably won't work, right? When we suggested putting this physics engine into cloud as an experiment, the team told us we were nuts, right? Because the bandwidth, we thought the latency would be too much of an issue. VR goes slow, you feel sick. You must have reliable, predictable round-trip performance. What they managed to measure was that certainly, first of all, the bandwidth was really good. This was coming from a data center in Frankfurt, but we've tried this now across different areas in Europe. They almost always got back within 60 milliseconds a full round trip, right, from the location to the data center. We've tried that in many different locations in universities, etc. So that was a very good and interesting result to me. I didn't expect it to be this good. The second one was that they showed very good linear scalability about being able to render the physics of the larger systems, calculating geometries, and getting the data off onto the network and onto the renderers near the VR headset. So this has been a very interesting project, which also has led to a spin out. The computational chemistry team have launched I'm not sure if it's a non-profit, but it's an open source company. So they've published all of the infrastructure into open source. We've seen 4 or 5 other collaborations now starting to use that code and also start to deploy it into cloud for different applications, including things like there's a team that's using it to build graphene layers and matrices, etc. as well. So that's an example project. Well, I talk about cloud, but not really talked much about what our cloud infrastructure is. So I'm going to go through this fairly quickly. So Oracle, like Google, Amazon, Microsoft, etc., is building a huge public cloud to run the world's Fortune 1000 and government services. Right, we've got about 400,000 customers, and almost every single one of them is in some form of conversation about how they move their enterprise IT into cloud. This is the fire that's going through the whole of enterprise IT. We build one architecture. We don't build different data centers for different customers. It's one architecture that supports all of those different customers running in the same place. So the red blocks here are examples of where researchers that I'm working with are running their various experiments, mostly in London, Frankfurt, Ashburn, and Phoenix in the States, but in some cases in some of these other areas as well. We connect each region, so a region like London, for example, will be connected to another region like Phoenix by dedicated dark fiber, but we never build one data center. We pretty much always build them in clusters of a minimum of 3, no more than 40 kilometers apart from each other. And that allows us to guarantee a degree of latency between them. So we look at guaranteed latency of less than 100 microseconds between hosts within a given AD, within a given data center, right, and less than half a millisecond between data centers within a given region. So, for example, in London, there's a data center in Wembley, there's another one in Slough, and there's another one in the middle of the city, connected as a single logical network. One of the things that we did to help move enterprise, but turns out to be very useful for research applications, is we rethought how we do the physical network in these data centers. We went back to 1950s clos architectures so that we have guaranteed, predictable networks, non-blocking. There's a leaf and spline network, so we can guarantee that within a given data center, there's never more than 2 hops between potentially millions of devices. So it means that we get predictable network latency at the lowest level. The second thing we did is we pushed virtual networking down into the physical layer. Now what that means is when you're doing a lot of virtual networking, you're consuming CPU cycles to inspect network packets. The busier the network, the more the CPUs are being used, the slower applications run, you get unpredictable application performance. So we push the virtual networking down into dedicated hardware in the physical layer so that the only packets coming through to a given server are intended to be for that server. And it takes the load off the CPU and satisfies a bunch of security risks that people had. The third thing that we did is we said, look, why is it when people need lots of cores are you running virtual machines and hypervisors in the first place? So we built the architecture of these data centers from day one on the basis and premise of bare metal. Okay, so you provide an operating system, you can bring it your own, it doesn't even have to have any Oracle software on it, and it will fire up a bare metal box, right, to be able to run on that network. So for high core count applications, right, there is no need for any virtual networking at all. The virtual networking, the network is in the physical layer. There's no need for the hypervisors running on the boxes. Of course, we can also provide hypervisors. So we allow people to create VM shapes if you only need a few cores, but it's layered on top of the whole notion that people can just use programmatic access to fire up bare metal machines. So those machines, we never, the history of public cloud started with commoditized hardware scaling out horizontally. We came from the other direction, right? We started off, Oracle acquired Sun quite a few years ago now, and we've been organizing their supply chain around creating high-end servers for public cloud. So the workhorses are 52-core X7 servers with 768 gig of RAM on them. Every single one of them's got 2-channel 25 gig NIC on them. So there's very fast network access and bandwidth within the data centers on there. And there's a second workhorse which we call Dense I/O, which has been pretty interesting for research applications. So this is a 52-core server, but there's 51 terabyte of NVMe storage on the same motherboard. Right, so for big data applications or for applications needing a lot of memory, right, for example, genomic databases, that we're working with teams on genomic databases, we're working with people with huge volumes of health data. I've got projects working on quantum computing simulation, able to use these very fast dense I/O boxes. Then there's obviously the multiple layers of storage, so very fast block storage, object storage, and archival storage going down that stack. So those are the top two. These are the top two machines on that network. On the right-hand side, we've got 2 generations of GPUs, bare metal again, but the ability to create VM shapes on top of them. The first is a bare metal machine with 2 Tesla P100s on it, and the latest generation is a 52-core machine with 8 V100s on it. So you can fire up clusters of these V100 bare metal shapes for doing things like machine learning, AI, and molecular simulation, and so on. There's a bunch of different storage shapes, an elastic file store with an NFS mount on it, block storage, which we see people putting Lustre and other fast parallel file systems to. A couple of people mentioned Oracle and HPC earlier. I should talk about this shape here. This is a fairly recent addition we added in the fall of last year. It's a 32-core X7 server running into latest Intel Skylake Platinum Xeon chips. Okay, but on that server is a Mellanox Rocky card. So what that gives it is it gives RWMA over converged Ethernet access. So if you build a cluster of say 30 of those HPC shapes, they'll be communicating across the network within the data center using InfiniBand style speed and latency. So you can quickly build up elastically HPC clusters comfortably up to about 1,008 cores. So this isn't exascale, but for a very large number of HPC and MPI applications, right, it allows people to use cloud to start pushing those workloads out. Another one we added fairly recently is this one on the right-hand side, which is a bare metal AMD machine. 64 cores, 30% faster memory channels than the Intel machines, which is quite nice for memory-intensive applications. But the nice thing about these is that they're half the price of the Intel chips. So if you're doing embarrassingly parallel applications, these can be a very, very cheap way to do that. And we're seeing quite a few researchers using that today. So putting it all together, you've got regions, availability domains, very fast physical network, virtual networking pushed into the network, and then very fast compute and storage shapes, on top of which you can layer virtual machines for smaller core counts. Somebody mentioned pricing. We keep the economics very, very simple so that people can calibrate how they're scaling up both economically and performance-wise. So we charge CPU hour rate, and it's the same CPU hour rate whether you're running VMs or bare metal, right? So CPU core hour. So typical rate's about 6 cents per CPU hour, per core hour. Sorry. The AMD chips are half the price of that, and the HPC chips I think about 7 cents a shot. So, and we don't charge to get data in or out of the cloud up to 10 terabytes a month. So that's the cloud. On top of the infrastructure as a service, we've also got a whole bunch of technologies that we're seeing researchers using at the platform level. So things like AI services, big data services, BI, as well as the cloud native app dev applications such as Kubernetes. We've got Kubernetes as a service here, so you don't have to do all the install and configuration. You can just deploy Kubernetes-based applications straight into cloud infrastructure. And this functions as a service technology as well, which allows people to define functions which can be deployed as Docker containers, okay, and have them automatically deployed, scheduled, and managed by the cloud infrastructure without having to set it all up directly. And again, we've got a bunch of research teams using that today. How am I doing for time? Where's Marco? Sorry, don't worry. Okay, so I want to talk about the Accelerator quickly. So the Accelerator program that I mentioned that we launched as support research is targeted at 3 different overlapping communities. Right, the first is researchers that are looking at computationally intensive or data intensive workloads. The second is educators, so we're supporting CDTs, we're supporting postgraduate training programs, we're supporting graduate programs, helping people introduce cloud native technologies, etc. And the final one is university spin-outs. In fact, Mariano, we've been supporting BioLM and other university spin-outs from those research areas. The program involves significant grants of cloud credits. Typical grant is about $25K. We've gone up to 100 or higher than that, or we've had grants that are smaller when people are trying to calibrate how much resources that they need. The second is, we don't think that providing cloud credits is enough. We provide direct access to the product engineering teams that the researchers might need to learn from. So, for example, the HPC groups or people working on big data, whichever the research project is. So it's very much a managed engagement with our product engineering teams because we want to learn from the process as well as provide the support to the researchers. Oracle, as I said, has got 400,000 customers. Many of them are very interested in the work that researchers are doing, and researchers are often interested in getting industrial partners on board. So we're connecting those threads together. We do a lot of work on jointly publicizing and promoting work. So that project I showed earlier with the molecular visualization, that was originally published in Science Advances, but we made sure it got into Nature, it got into BBC Science programs, we got it into New York Times and Wall Street Journal and Forbes as well, by connecting the university's press and comms with Oracle's global marketing and press and comms, etc. Another key thing is providing early access to hardware. So we made those HPC and AMD shapes, for example, available, and new GPU shapes available to researchers before we make it available to the rest of the Oracle community, because there's a very useful mutual learning experience there. Examples of the kinds of projects we're very involved with the LUX-Zeppelin search, which is one of the big 3 challenges in particle physics at the moment. We've got people simulating billions of photons, right, going through the equipment to be able to look for a dark matter with this one. We've recently getting to the end of the first phase of a very interesting project with MRI based at the Elizabeth Blackwell Institute. 40 years of longitudinal health data, right, taken from the point that someone is born. Literally, they're registered into the program. Every sneeze, cough, flu, etc. that they've ever had, now being correlated with the genome data because we've sequenced, or the Elizabeth Blackwell Institute has sequenced the DNA of all of these patients, right, after 40 years of health data. And so they're using that database, they're using that data to be able to do causality and causation studies, and then relating it back to the genome data. This was using the dense I/O shapes, for example, taking that 50 terabytes of data and then just putting it straight into NVMe storage. We've seen all the queries go up between 10 and 100-fold in terms of speed. So something that took an hour is taking 40 seconds. So that's been a very, very interesting project to work through. We've got some cancer research activity going on at Nottingham Trent. There's this very interesting project on the nicotine receptors. So this is simulating a very, very long protein, being able to take that simulation, break it down into about 1,350 5-nanosecond simulations on using GROMACS. They were looking at 9 months, minimum 3 months, and probably 9 months to schedule that through the Blue Crystal supercomputing infrastructure at Bristol University, because it's a lot of jobs to schedule and the team could do 10 in parallel at a given time. We helped them create a cluster which automatically scaled up 152 core nodes, executed all the jobs in 4 days, right, and then closed down the cluster. So in terms of the compute time, the machines were faster, so it went quicker as well. But they were able to get in 5 days what would have probably have taken about 6 months minimum to get the results from. So this was a really interesting way of how not just being able to burst to cloud, but being able to use the elastic scaling of cloud rather than queuing jobs into cloud. It was changing the way the research was doing. We've got some complex fluid modeling and simulation workflows going through here for being able to see how air moves through electronic closures so that we can change the layout of circuit boards, for example, on servers going into data centers, to be able to automatically reduce the energy consumption within data centers. And we've got this great project with Christopher Woods' team at the University of Bristol using Jupyter Notebooks to be able to automate molecular dynamics workflows. The program itself, I won't go into too much detail on the second one. The program itself has got a very simple application process. We ask about 10 questions about a given research area. We look for projects that are fairly quick to get initial results. We're really looking for programs where people are looking at using cloud. They're looking at getting results within a 3 to 4 month time frame, at least for the initial phase of the project. They're looking for publication, but they need acceleration because they can't get access to the resources they've currently got, or they need to be able to explore architectural approaches that they can't do on their existing infrastructure. So we typically will make a grant within 2 weeks of the application process going through on a rolling basis as we go throughout the year. So I'll be very interested if there are people here that would be interested in collaboration. Please come and talk to me at the break, or have a look at the slides afterwards. There's the links into the Accelerator program. So hopefully I haven't gone too far over time. So if there are questions within there, okay. Thank you very much.